Okay, you guys just missed a lot, sorry. Read the notes that I put up. So if you weren't in class and you're now seeing the video, I'm sorry. Everybody else in this class, all the rest of the that came to class, have part of the lecture you're missing, and you'll have to read the notes. I can't wait for October 5th. I can't wait to October 5th. Okay, stand up again, stand up again, stand up again. All right. Grab two objects in your room. Grab two objects in your room. Any two objects. Grab two objects in your room. Get two objects. Okay, put one object somewhere in the room. Put one object somewhere in the room. Okay, it needs to be able to stay where because you're going to leave it. You're going to abandon it like a child. Okay, so you've abandoned that child. Now go put your other child somewhere else in your room. Go put your other child somewhere else in your room. Okay, now pick an origin, 0, 0, 0, as being one of the corners in your room. Pick an origin being 0, 0, 0, probably on the floor. It's probably going to be a little easier. Pick one of the corners on the floor as being the origin in your room. Okay, now I want you to the best of your ability in terms of feet, describe where your two babies you just left are in your room. So sit back down, try to think in terms of feet from that origin. You got 3 coordinates. Describe where you left those two babies. If you had to have somebody go pick them up. Try to figure out, roughly in terms of feet, where they would be in your room from that origin. Okay. I'm picking on, who am I going to pick here? Zachary. Go ahead, tell me where your location is. Where's your babies? Where's your first baby at, roughly? Where's your first baby?
I said 2 foot or 2, 2, 3.
2, 2, 3. Okay, so where's your origin in your room, Zachary? Where's your origin in your room?
Just off to the left.
It's over there. So go to grid view. Go to grid view. All right, can you guys see Zachary? Can you see Zachary? Can you guys see Zachary in the grid? Wave your hand, Zachary. Wave your hand. Okay, there's Zachary. His first baby was at 2 feet, 2 feet, 2 feet, 2 feet, 3 feet. Okay, so he pointed to the corner. Point to your origin again, Zachary. Point to your origin. So it's over there. So he's gonna go 2 feet down the. He's gonna go 2 feet down the x-axis. Then he's gonna go 2 feet over on the y-axis. Then he's gonna go 3 feet up on the z-axis. So that's it. That's one point in the room. Where's your other point?
I said it was 6, 5, and 4.
6, 5, and 4. Okay, so now he's going out 6 feet along that corner. Then he's shooting over 5 feet, probably past himself. I mean, it's probably beyond him. And then he's sticking up somewhere 4 feet in the room. So I don't know what you've got in that room that's 4 feet tall, but that's pretty cool. Maybe a headboard or something like that. Okay, now look around the room at the two objects you guys planted. Can you visualize a straight line running between those two objects? Can you visualize a straight line running between those two objects? Now imagine I said things like this. I want you to cut a 2x4 that will reach one wall to the other wall and run through those 2 points. But you can't use a tape measure. Would that be hard? But these are some of the things that we're going to do. Some of the things that we're going to do. Okay, stand up again. You need this. Okay. Stretch. Okay, sit back down. Now let's go back to an equation of a line where we're comfortable. Let's go back to the equation of a line where we're comfortable in two-dimensional space. There we've kind of lived and we've been pretty comfortable. This axis would be that axis would be the two-dimensional space. Y-axis, this axis would be the x-axis, and then now we're pissed because we flipped it around on us where this is the x and this is the y, the z points up. But in two-dimensional space, this is what we have. Now let's just plot 2 points. Plot 2, 3, plot 2, 3, plot 2, 3, and plot 5, 7. Plot 2, 3, and plot 5, 7. And then what I want you to do is I want you to graph the line that goes between those 2 points. 2, 3, and 5, 7, and graph the line that runs between those 2 points. How many people have a picture that looks like that? How many have a picture that kind of looks like what I just drew on the board? Okay, now let's go back to high school, and they would say, okay, find the equation of that line. Find the equation of that line. Don't do that. How many times were you asked to find the equation of lines? How many times were you asked to find the equation of line? Think about high school. Find out where the 2 lines intersect. Do you remember that? Doing that? Remember finding out where the 2 lines intersect? And then they beat the hell out of that by saying, okay, we're going to use the elimination method. We're going to use the substitution method. How much of high school was about lines? If you go back to what you dealt with in high school, how much of it was about lines? Y equals mx plus b. But you know, you don't really geometrically understand where the equation of the line came from. You vomit out y equals mx plus b, or if you even know it better, your point slope formula, y minus y1 equals m times x minus x1. You're like, I'm a genius. But you don't really ask geometrically, where does this come from? It's because it's never really properly been written down for you. If you're talking about a line, you're really talking about a set. And that's what's not told to many students. You're talking about the set of all the ordered pairs that satisfy such that the second coordinate in that ordered pair is equal to m times the first coordinate plus b. When they say write equation of line and you write down y equals mx plus b, yes, that's what we write down. But we don't really think of it as a set of points that obey this equation. But you're going to be screwed when we go to three-dimensional space if you don't think about it as a set. Because the equation of a line in three-dimensional space, the equation of a line running between the 2 objects in your room is going to look very different than an equation of a line that you're used to writing in 2-dimensional space. And this is the way I'm going to try to get you to follow me with this. Let's just pick any other point on the line. So I'm going to pick an arbitrary point on the line, and just so it works out a little bit more comfortably for you, I'm just going to pick it somewhere between the 2 points that I have there. So you guys do the same thing. Pick an arbitrary point on your line. And let's suppose it's in S. Let's suppose it's in S. It's an arbitrary point that's in S, so I'll just mark it as xy. So I'm just going to mark it, since it can be any point on the line, as xy. Now what I want you to do is I want you to draw that right triangle. What I want you to do is I want you to draw that right triangle. I just drew a right triangle where I went straight over from 3 and I went straight up from 5. You're like, Dr. Warren, we've drawn this triangle before. Yeah, that was for the distance formula, when we were calculating our distance formula. Now, how many people are pretty comfortable they could find this leg of that right triangle? How many people are pretty comfortable they could find that leg of that right triangle? I mean, just by the numbers that are on the board. How many people that are pretty comfortable they could find that leg of that right triangle? What's that distance? 4. Now, don't get angry with me. I'm going to write it as 7 minus 3. You're like, Dr. Warren, that's 4. Write it as 7 minus 3, damn it. Similarly, in the same kind of form, write down that leg. Write down the distance that represents this horizontal leg of that right triangle. In the same kind of way, like we wrote 7 minus 4, what represents the distance of this horizontal leg? And you guys would say
5 minus 2.
5 minus 2. The difference of my 2x coordinates. This is the difference of my 2y coordinates. This is the distance of my 2x coordinates. Now, you're not going to be able to see this because we're on Zoom. Okay, you're not going to be able to see this, but draw this little right triangle where we do the same thing. Drop down. Draw that little right triangle. This little one from that other point. Similarly, give me an expression that represents this distance. Similarly, give me an expression that represents this distance and this distance. I'm not going to be able to write it where you can see it, but I've got the point xy, I've got the point 2, 3, and I want an expression that represents this distance and that distance. Now show me what you have. Show me what you have. Hold up what you have. Hold up what you have. I want to see what you guys have there. I want to see what you have there. Oh, sweet. Cosmo, drop yours down a little bit more so I can see. Cosmo just got, there it is. Perfect. There. Go to grid view. 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 Okay, look at Cosmos. You look at Cosmos over here. Look at Cosmos. So if we're looking at it, he's calling that bottom one x minus 2. Do you see his x minus 2 there? X minus 2. And he's saying this other one, this other side is y minus 3. The other side is y minus 3. Okay, go back, make me number 1. Thanks, Cosmo, you're awesome. So he wrote this is y minus 3. And this little baby side here as x minus 2. So if you didn't write that, write it now. Now look at these two right triangles. Do they both have right angles? Look at the little baby and the big one. Do they both have right angles? Do they both have right angles? Do they share a common angle? Do they share a common angle? Does the big right triangle and the little right triangle share a common angle? Well, what does that tell me about this angle and that angle? What does that tell me about this angle and that angle? Geometrically, then what must be true about this angle and that angle? They're the same. So mark them as the same. Okay? If something's going to be complicated in calculus, chances are it's going to come from similar triangles or Pythagorean theorem. I've got these two similar triangles. So their corresponding sides are going to be, it starts with a P. Their corresponding sides are going to be pis. No, that's not the word I'm thinking of. The corresponding sides are going to be proportional. Say that.
Proportional.
Okay, so like for example, I could say y minus 3, baby side, over big side, 7 minus 3, would have to be equal to y minus 3 over 7 minus 3 would have to be equal to
X minus 2 or
X minus 2
over 5 minus 2. Proportional. Little side over corresponding big side. Put a box around that. Put a box around that. This is called the symmetric form of the line. It's not taught in high school often. This is called the symmetric form of the line. And all the rest of the forms of the line follow from this. All the rest of the forms of the line follow from this. Like, for example, I'm going to do a little bit of algebra. You're in which calculus now? You're in which calculus now? Just to help me out. You're in Calc 3. Okay, you should understand this algebra. Y minus 3 equals 7 minus 3 over 5 minus 2 times x minus 2. All I'm doing is taking this guy to the other side. Is this true? If I'm here, could I get there? If I'm here, could I get there? But guys, that's the what of the line. I just put a box around it. That's the what of the line.
the slope.
The slope. This is your point slope formula. This is your point slope formula. And if you take the 3 to the other side, you get your slope intercept formula. You now take the 3 to the other side, you end up getting your slope intercept. This is the symmetric form of the line. Now let's look at it again. It's y minus y1 over y2 minus y1. X minus x1 over x2 minus x1. So write that formula down. Write that formula down. If you have 2 points and you want to get the symmetric form of the line, it's y minus y1, and I'll probably change it around here, over y2 minus y1. I'll put the x's first. X minus x1 over x2 minus x1. Now it takes some significant drawing that I cannot do on the chalkboard in perspective enough for you guys to get the similar triangles, to see the similar triangles that extends this to 3 dimensions. The line that would run between the 2 points in your room. The line that would run between the 2 points in your room. If I wanted the equation of the line that would run through Zachary's 2 points, if I wanted the equation of the line that would run between Zachary's 2 points, here's my point 1, here's my point 2, this would be the equation of that line. It doesn't really matter which I call point 1 or which I call point 2, but it would be x minus 2, if I call this, x minus x1 divided by 6 minus 2 is equal to y minus 2 over 5 minus 2. You're like, hey, Dr. Warren, that's awesome. That's the equation of the line. That's the equation of the line in 2 dimensions. Oh, we're not done. We're not done. Which is equal to, you're like, damn it, z minus 3 over 4 minus 3. Simplifying a little bit, it would be x minus 2 over 4 equals y minus 2 over 3, which is equal to z minus 3 over 1. That's Descartes' formula of a line. That's the Cartesian form of a line in 3 dimensions. Okay, now you look at your 2 points. Your 2 points were different than Zachary. I did Zachary's work for him. Okay, Zach, you're done, man. I finished for you. You guys write down the equation of the line that runs through your bedroom. Write down the equation line where you use some corner as the origin. Write down the equation of the line that runs through your bedroom. Now, as long as you're consistent, it doesn't matter which point you call point 1 and point 2. You know, you could have said x minus 6. You could have said x minus 6 over 2 minus 6. You could do the same thing. X minus y minus 5 over 2 minus 5, and so on and so on. Okay, now let me show you how to use this equation of the line. Okay.
What if your y2 minus y1 is 0?
What if your y2 minus y1 is 0? Oh, such a sweet question. What if your y2 minus y1 is 0? Ooh, what does that tell you about that line in your bedroom?
They're in the same pair. I'm not parallel.
Yeah, good, Michael. Yeah. They're in the same plane. If they have the same y coordinate, it means they run. Think about our y-axis. If they have the same y coordinate, they're going to lie in a plane that runs perpendicular, that runs straight down this room. It's going to lie in a plane that's like this, and then we're just graphing our regular equation of a line in 2 dimensions. It's just that it's here, not in my xy plane. It's so much fun. It really is so much fun. I mean, and I don't have enough time to have it be totally fun. I need you guys 8 hours a day, 7 days a week. But I'm going to like Zachary. Imagine that. Okay. I want to find another point on Zach's line. I want to find another point on Zach's line. So I'm going to head in his corner. Here's his equation of a line. Okay, I'm going to head in his corner. Okay, and I'm going to say, okay, I want to know the equation where now, Zach, I want to hit your line, but I only want to go 1 foot in the x direction. Okay? And I want to go 1 foot in the x direction. So if I plug that into my equation of my line, so imagine Zachary. Zachary, look at your corner. Go out one in the x direction. So imagine now, Zach, you've got a plane. Imagine that you've got a plane sitting straight on the floor looking up. Do you see where that plane will hit your line? Can you kind of visualize where that plane's going to run into your line? That's what we're trying to find. We're trying to find that point. We're trying to find that point where we hit that line. So we plug this into our equation. So I'm going to come over here and I'll plug that into my equation for x. So I'd have 1 minus 2 over 4 is equal to y minus 2 over 3, which is equal to z minus 3 over 1. But now this is negative 1/4. And like Dr. Warren, what black magic did you do? I plugged 1 in for x. Do you see this equation? Dr. Warren, quit covering up the z. Do you see this equation? Could you solve this equation for y? Could you solve that equation for y? Could you solve that equation for y? And then what if I did that? Could you solve that equation for z? Could you solve that equation for z? And then, so you do that. You solve the first equation, hide that, for y. Solve the second equation for z, and tell Zachary where exactly his point is on his line in his room. Tell him exactly how he could start at his origin, and go over and hit that point in his room. Okay, and hopefully you're getting something what I got. Hopefully you guys are getting close to something I had. You would have y equals 5/4, or 1 1/4. Did anybody get that? Did anybody get that? Okay, and z's equal to 3 minus 1/4, which is 11/4, So then, Zach, you could just turn those into decimals. Grab your tape measure, okay? And then you could go out the x direction 1, go over the y direction, 1 1/4 of a foot, and you go up 2 3/4 of a foot, and that'll be a point that sits right on that line that runs through your bedroom. It's totally cool, guys. It's totally cool. And we're just talking about lines, not roller coasters, which is where we're heading. Okay. So give me another equation of a line. Just write down, give me another equation of a line. A different one than what you have. Make up your own. Give me another equation of a line in three-dimensional space. Give them another equation. Write down another equation of a line in three-dimensional space. In symmetric form. Okay, Greer, what do you got for me? What's your line? What's the line you just made up?
I did 0.1235 and then 0.2452.
Okay. I like where you're going. You're giving me 2 points. And then you could find the equation of a line. But I didn't want you to go through that much work. Sorry, Greer. I should have been more. I should have said, don't pick 2 points. Just give me an equation of a line. Jake, what do you got for me?
X minus 3 over 5 minus 3.
X minus 3 over 5 minus 3, and I'll just 5 minus 3 is 2. I'll just keep going that way. And then
Y minus 4 over 2.
Y minus 4 over 2, and then
Z minus 2 over 6.
Z minus 2 over 6. Is that the equation? Is that an equation of a line in three-dimensional space? When you look at that, guys, is that the equation of a line in three-dimensional space? Now the problem is, this is a little tough to work with. And this is where vectors come in and really help us. This was long before vectors. This was long before Gibbs. Gibbs' vector analysis that we're learning really came around 1900. Descartes was way before 1900. I mean, 1900 was only like a grandma and a half ago. If you count back in grandma lives, it was only like a grandma and a half ago where vector analysis is where we're at. So now I want to talk about something that represents a line, but in terms of vectors instead of my symmetric form. So now I'm going to introduce a line here in three-dimensional space. So now I'm setting my line here. Can you guys see my line? Can you see my line? Can you see the line there? Okay, so now I'm going to talk about how to find the vector form of a line. I could pick 2 points. In fact, I have 2 points here. What are my 2 points? 1, 2, 3. Real clever, Dr. Warren. And then what's the second point?
3, 1, 5.
3, 1, 5. They don't lie on this line. But I want to talk about how could I find a vector form of this line. So get ready to write this down. Write line. You should be able to all do that. Write line, the word line. Now write vector A plus scalar t. And like Dr. Warren, you can't add a vector and a scalar. You can't add a vector. I'm not done. Scalar t times vector d. A plus TD. Say that.
A plus DTD.
Okay, that was one person. Hands on the space bar, hands on the space bar, hands on the space bar. I say line in this class. I want it to be Pavlovian. I say line, you say.
Plus DD.
Yeah, that was one person. Hands on the space bar. I see too many red microphones. I see too many. Put your hands on the space bar. A plus TD. I say line. You say
A plus TD.
line.
A plus TD.
Line.
A plus TD.
Line.
A plus TD.
Okay, now beside A, write position vector. Because it positions the line somewhere in three-dimensional space. Beside A, write position vector. And beside D, write direction vector. Because it directs the line. A positions the line, D. A positions the line, D. A positions the line, D. Directs the line. Okay, so I've got my line here, and I've got my origin here in my x, y, z. This is x, this is y, this is z. So I'm going to pick A. Since it's a position vector, it's always going to be, its butt's going to be at the origin. Don't you fall, little eraser. Right. And then it points to a point. It points to a point that's on the line. Can you see how this green vector's pointing to this point on this wavy line? Can you see that? And I mean, because this is a fixed vector, I might have another one that points down there. There's infinitely many position vectors. There's infinitely many points you could point to. So there's my position vector. That's A or D. This green would be A or D. Green would be A or D. A. Now I need a direction vector. And so here's going to be my A, and then my D is going to be maybe like this. My direction vector lies on my line. My direction vector lies on my line. So now, let's pick a value for t. I say line, you say, I've forgotten already, Dr. A plus TD. T is 1. T is 1. So it'd be A plus D. A plus D. Where's the vector A plus D in this room, in my classroom here? Where's the vector A plus D in this room? The geometry. Where's the vector A plus D in the room?
Going from the origin to the tip of the blue.
It goes from the origin to the tip of the blue. It goes from the origin to the tip of the blue. Now imagine I say A plus 2D. A plus 2D. Now suddenly, if I do 2D, my blue vector's now twice as long. So imagine that this still goes like this. Now can you visualize A plus 2D? Can you visualize A plus 2D? It's going to start at the origin and then go to the tip of the blue vector. Now what if I do this? What if I do this nightmare? Woo-hoo! Woo-hoo! This would be A plus negative 1D. And it would start at the origin and go to where the blue vector is. What if I let t be any scalar at all between minus infinity to infinity? What if I let t be any scalar at all? Do you see how you would get a position vector starting at the origin and running along, pointing to every single point on the line? If I let a scalar t run through minus infinity to infinity, I'm going to have a position vector that's going to point to every single point on my line. And that's how that's how a plus td represents a line. Okay. Draw an xyz coordinate system. Just draw an xyz coordinate system, and I'll do the same thing. I'm now going to help you guys at least get it down on paper. I'll do the same. Okay, this would be the which axis? That would be which axis? This is, you're not. Oh no.
Z.
X.
Y.
Y. Now I'm going to pick 2 points. I'm going to pick 2 points in my three-dimensional space. So maybe one is here, and the other one's there. I'm kind of visualizing this one comes out, and then goes up, and goes over. This one goes further out, further up, further over. Okay, so I've got these 2 points here, and now I want to put a line between them. So you put your 2 points, just like what I did, and draw the line. You should be able to do that. Draw the line, draw this line that we're kind of like using a drawing to represent what we have here with this thing. Okay, when I say line, you say, Dr. Warren, you're going to beat the hell out of me. A plus TD. We need a position vector and we need a direction vector. How many people see, if they give me 2 points, like 1, 2, 3, 3, 1, 5, getting a position vector ain't so bad. How many people realize A is not that hard to get if they give you 2 points? You really have 2 options. You could either start that one, run from the origin and go to there, call that A, so mark it as A. So it's that vector there. Like over here, if I was looking at these 2 points, I could make either one of these. I could turn either one of these into a vector. Focus. What I'm going to say is really important. Focus. How many people realize these aren't the same 2 things? How many people realize these are not the same 2 things? This is a vector. This is a point that's on the line. A is a vector that points to the line. Do you get the difference between the 2? Okay. There's this other one that we could use too. I'll call it B so it doesn't get confused with A, and you should probably do the same. That could also be a position vector. So like B could be the vector 3, 1, 5. How many people can see visually a way? Look at the drawing. How many people can visually see a way to get a direction vector? If you have 2 position vectors, can anybody think of a way that we could get a direction vector that would lie on the line? Could anybody think of a way, geometrically, using the crap we've invented in vector analysis, that we could find a direction vector? Can anybody think of a way that we could find a direction vector?
You do like A minus B or B minus A?
You could do A minus B or B minus A. I'll probably draw it as b minus a. So mark b minus a, mark b minus a. Now, you put the arrow the right way. You put the arrow on b minus a the right way. You draw in the arrow. Which side does it go on? B minus a. You mark the arrowhead. Does the arrowhead go on this side where A is, or that side where B is? Which side does the arrowhead go on the vector? Is it here or there? There or here?
There.
It's there. It's there. It always points to the guy that you're not subtracting. You're subtracting it from B. The result is going to be B if you add these two vectors together. It doesn't, I mean, guys, look at it visually, head to tail. Does A plus B minus A equal B? Visually, geometrically, does A plus B minus A give you B? So it's not that bad. It's not that bad. You start doing it enough, it makes sense. Okay, so over here, there's my position vector. Find me a direction vector. Find me a direction vector that could help me get the equation of the line. Find me a direction vector that could help me get the equation of the line. You guys in video land should be doing this too. You guys in video land should be doing this too. A vector's an order triple of three real, vector's an order triple of, Robert's, everybody's like, a vector's an order triple of three real numbers. What are the three real numbers you have in your vector? What are the three real numbers you have in your vector, for your direction vector? What are the three real numbers you have? What's the first real number?
2.
2. Anybody else get 2? Anybody else get 2? Raise your hand. Okay, how about your next component in your direction vector?
-1.
-1. How about the next one? How about the next one?
2.
2. Okay, so what would the equation of the line be in vector form? What would the equation of the line be in vector form? What would the equation of the line be, this line between these 2 points be in vector form? I say line, you say, that'll help you a lot. A plus TD, so write it down, A plus TD. Okay, now write it down as a single vector. Write it down as a single vector. Write it down as a single vector. Instead of writing it as A plus TD, write all of that as a single vector using your scalar multiplication and vector addition. So the first component would be what? The first component would be what?
1 plus 2t.
1 plus 2t. 1 plus 2t. The second component would be 2 plus -1 times t, or 2 minus t. And the third component would be 3 plus 2t. The third component would be 3 plus 2t. And we mark this as r of t. We mark this as a function r of t. And this is my equation of my line. This is my equation of my line that we're going to work with almost. We'll work with the symmetric form a little bit, but we're almost always going to be working with a plus td. We're almost always going to be working with a plus td. Okay, I'm not going to write it down, but just like in 2 dimensions, I don't care what I say now, you won't focus. It's been over an hour of me yapping. What time does class end? Not now, I finally know. What time does class end? Not now. At 11, not now. Okay. If I say y equals 3x plus 2, can you visualize a line in 2-dimensional space? If I say, well, I mean, have you been hit enough with that? If I say y equals 3x plus 2, can you see a y-intercept of 2? Can you plot a y-intercept of 2 and give yourself a slope of 3, run over 1, rise 3, draw your line? But again, it's a set of points. What did I just say? You're just looking at my forehead. What did I just say?
Points.
A set of points. This is freaky looking. A set of points. I look like a bull. Learn. Okay, it's a set of points, x, y, that satisfy that equation. In the same way, Dr. Warren, I'm not listening to you at all. In the same way, when we write this down, a plus td, or in this form, we're talking about a set of points that satisfy for every t that the x-coordinate of the point is 1 plus 2t, the y-coordinate of the point is 2 minus t, and the z component of the point is 3 plus 2t. Now guys, this is much easier to code than this. This is much easier to code than this. Visualizing this is kind of hard. The symmetric form that Descartes gave us is kind of hard. But visualizing and coding this is a whole lot simpler. So now, go to Canvas, and open up that plotting routine. Or go to Canvas and open up that plotting routine. And I'm going to go to the front of the room. Okay. So the first thing I want you to do is get rid of that graph of that surface. You're not ready for a surface. So just push an X, and get rid of that graph. Okay, the next thing I want you to do is click this thing. Click this blue grid here. And I want you to change X min. Can you guys hear me through the tunnel? Can you hear me through the tunnel up here?
Yes.
Thank you. Change it to from -2 to -10. Same thing in the Y and same thing in the Z. Also change your tick marks to be 2 instead of 1. Change your tick marks over here to be 2 instead of 1. So -10, 10, -10, 10, -10, 10, and then 2, 2, 2. Do not change these. Bad things happen. When you're done, just hit graph. If you type like me, it's going to take you forever. Then just kind of move the thing around, kind of fun. Just kind of, when you're done, just kind of move it around so you're helping yourself in 3-dimensional space. Okay, the next thing, let's get rid of this. So let's just, once you've done, just get that out of the way. The next thing I want you to do is I want you to come over and go to select, and go down to vector. Go down and select vector. And I'm just gonna blow mine up here. I'm gonna do this one first. Okay, so let's do this one. Let's set our position vector. Go back and look at your notes. Who was the A? Who was the A? What was the A?
1, 2, 3.
1, 2, 3, it's a position vector. So its butt here is at the origin, 0, 0, 0. So you set your vector. Set your vector 1, 2, 3. Make the color red. Make the color red, kind of like what I did. And then when you're done, it'll take a little while. When you're done, just click the little check mark here and plot your position vector. So there's my position vector. Now let's plot our direction vector. What was the direction vector, guys? What was the direction vector? What was D when you guys did it? What was D? What did you have?
2, -1, 2.
2, -1, 2. Now listen to me. Okay, I'm now back near the mic. I want you to put the butt. I want you to put the butt of D at the head of A. Put the butt of D at the head of A. So go plot another vector. And I'll come back here and do the same thing. Plot another vector. But down here in the initial point, I'm putting the butt 1, 2, 3, the butt here, and then I'm plotting my direction vector there. And make it blue. Make it blue. So 2, -1, 2. And when you're done, just make it show up. When you're done, when you got it, make it show up. And then do the same thing, spin it around. There's kind of your A plus D. So where would the vector A plus D be, guys? Where would the vector A plus D be? A plus 1D. Well, put your cursor at the origin. Put your cursor at the origin, and then run it up to the head of that blue vector. Put your cursor at the origin, and then run it up to the head. That points to one point on the line. Okay, I'm going to now minimize this for me and come back and look at you guys. How many people are with me? How many people have that? Amanda, how many people have that? Raise your hands. How many people have that? Okay, awesome. You guys are great. I know this takes a lot of time. I know it takes a lot of time. It's worth it, though, for you guys to be able to visualize it. Now, goes to select. Go to select, and I want you to go to space curve. And click on space curve. Click on space curve. This R of T, space curve. Now, look at the last form in your notes. Look at our R of T. Go look at your notes. Look at the R of T. What was the x coordinate in that R of T form that we had? What was the x coordinate in the R of T?
1 plus 2t.
So put that in the x component of the space curve. You can see here it says x of t equals, and then I put it here, 1 plus 2t. So you do the same thing, and similarly put the other two in the y of t and the z of t. And make your color green if you can. Make your color green. And when you're done, let's make it visible by just clicking this box. When you're done, just make it visible. How many people have a green line? How many people have a green line yet? You guys have a line? Then move it around. You take a look at that line. Move it around. You can kind of see the line. Now notice the parameter t, that scalar is running between minus 10 and 10. So it has an ending point. It has an ending point and it has a starting point. But there's your line. There's the line. That r of t keeps sweeping from the origin and points to points on the line. Now this is kind of fun. Click trace, come down here, go down into your thing and click trace. And then hit animate. And you can actually see it run along with your position vector and your direction vector. It's actually running along there, where the head of that black vector from the origin is kind of what you have. Does this help you visualize it? Does this help you visualize it a little bit? When we say a plus td, and now let me see if I can stop it. No, I can't. Okay. Maybe I'll have it stop in the middle. You're only going to 5. Okay, you're going to, oh, come on. Maybe I'll change it here, 5. Okay, so if I'm thinking about what r of t is, what did I just say? Because I know I'm in a tunnel.
You're thinking about what R-T.
It starts at the origin, and ends at that black vector. It's positions to a point on the line. Okay. Does that help? Does that help you visually see a line? Does that help you visually see a line? Okay. Would it be nice to be able to go between the two forms easily? Would it be nice to be able to go from the symmetric form to the vector form, or the vector form, or the vector form to the symmetric form? How many people would like that? Raise your hands. How many people would like an easy way to do this? How many people would like an easy way to do this? I know. Poor Luke. Luke, man, you look like I'm just beat the hell out of you. That's the way you look right now. You look like I just beat the hell out of you. Okay. Jake, you're not raising your hand, right? No, all right, yeah, I wasn't sure what was going on there. Okay. Yeah, Nick, I saw the double hand. I like that purple thing going around your room too, Nick. That looks pretty awesome. I want that. Okay, this is the symmetric or the vector. You should be able to know. If you've been in class today. Symmetric or vector? Symmetric. Suppose I had this, and I wanted to go to either one of these. Okay, now watch. This was really x minus x1 over x2 minus x1. Right? I mean, you think about the way we laid those out proportionally. The second one was really, help me out. They're mowing outside. Help me out.
Y minus Y1.
Over
Y2 minus Y1.
y2 minus y1. And then you're like, Dr. Warren, damn it, I got it. You're so boring. Z minus z1 over z2 minus z1. I gotta drop my line here. Sorry. Woo. And you're like, Dr. Warren, what was the x1? What was x1? What was y1? What was x2? What was y2? What are all these things? They were points. This was the x coordinate of the first point, the y coordinate of the second point, the y coordinate of the first point, the z coordinate of the first point. This was the x coordinate of the second point, the y coordinate of the second point, and the z coordinate of the second point. If you have a point on the line, like 1, 2, 3, can you get a position vector pretty easily? If you have if you have a point on the line, can you find a position vector? So if I'm looking here, look up here. Look in the x1 location. What number is that? Look in the x1 location. What number is that? 3. So I can get a position vector. Look here. What would the y coordinate of the position vector be? I'll help you. What would the y coordinate of the position vector be?
4.
Oh, good, good. Okay. How about the z component? How about the z component? 2. Two points, 2 points. Draw nothing, draw nothing, draw nothing, draw nothing. I'm the artist. So we just got that. There's A. There's our position vector. Now we want our direction vector. But if you look at this as being B, what was D again? If this is A, if this is pointing to this point, and that's pointing to that point, what's D? What's D? What's D? What's D? What's D? What's D? B minus A. Or x1 minus x2 minus x1, y2 minus y1, z2 minus z1. But look in the bottom of the formula. How sweet is this? What do you have in the denominator here? What do you have in the denominator?
X2 minus X1.
Y2 minus Y1.
And
Z2 minus
so if you want the direction vector, you just look at the denominator and you go, oh, the direction vector is 2, 2, 2, 2, 2, 2, 2, 2, 6. So you want the vector form of the line? I say line, you say
A plus T.
A plus TD. It's just going to be 3, 4, 2 plus T times 2, 2, 6. Then I can say, oh, go plot it. Go ahead, go to the plotting. Don't. I can say, go to the plotting routine and plot that thing. Look at it in comparison to the one we just had. Okay, I'm going to let you leave now, since I'm past time. I want you guys working on the homework in 12.5. In 12.5. Your quest will be on lines and cross product mainly. Lines and cross product mainly. All right, you guys are great for putting up with me. Thanks for coming out and playing. Okay, I'm coming out to the sandbox, Calc 3 sandbox. I will see you on Monday. And I'll see you guys on Monday. You should have been here. It would have been so much better.
Weekend, thank you.
See you guys. Safe weekend. Safe weekend.
Hey, Professor Warren, could you tell me, for the area of the shadow of the parallelogram, I didn't write the top of the equation. Do you know that?
The shadow.
Yeah, it was A cross B divided by A cross.
Oh yeah. Okay. Michael, if you have like, let me get here. Imagine that I've got 4 vectors.
Yeah,
This is
never seen the shadow of a parallelogram.
And I want another one here. Here's C, here's D. And I'm going to create this parallelogram where I reproduce D and C. So there's this parallelogram kind of sitting like this. And I want to cast it down. I want to look at the shadow down here in this plane. And I'm like, how much area is in there? This is the way
I was drawing that and I didn't get the top of the equation.
So if you want to cast this shadow down here, what you do is you do A cross B divided by the norm of A cross B, dotted with C cross D.
Yeah, I got that, but then what's A times, I got the bottom.
Okay, so now we're just using this flashcard. If you have 4 vectors and you want to calculate this cross product, and suppose you had to do that on the quest. This is hard. I mean, the cross product formula is pretty hard to remember, let alone doing it twice and then taking the dot product. But we can show this is equivalent to A dot C. It's almost like foiling. It's almost like foiling times B dot D. Then there's a minus sign. Then there's a minus sign. And then you just take A over to the other guy, A dot D, and you match B with the other guy, B dot C. And that formula is a lot faster because it's dot products instead of cross products.
And then didn't that equal something like over the
Oh, if I go back to this, I can just divide it all. I can just divide it all by this scalar.
Okay, I see.
And so that would give me, that number, when I calculated it, would unbelievably give me that area, which is so cool.
Yeah. Oh, and just another question. Yeah, that is really cool. I've never actually seen that picture before. The projection of the parallelogram. And the line too, all the vectors going to the line. I mean, I've seen it, but I never saw how it's derived. That was real cool too. But so for the in 2 dimensions, the x. How do you, where does the negative come from? Because it was, I was going to ask it last time, like the negative intercepts, where does that come from?
The negative on... let me see, I'm gonna come up here and see if go ahead, hold it up there. Michael, hold it up again, let me see. Okay, yeah, so... let me go back. If I draw a number line, and I pick 2 points on a number line, like maybe 7 is one value, and -2. Then I ask, what's the distance between 7 and -2?
It's 9, right?
It's 9, it is 9. But if you were gonna explain an operation that you would use to get that, you would take the point that's furthest positive, 7, minus the point that's furthest to the left, and that gives you the 9 that you wanted. So you can use the subtraction, you can use the operation of subtraction to get the distance.
Gotcha.
All right?
Awesome. All right. Thank you. You have a good rest of your...
You too, Michael, you too.
Thank you. Oh, weekend.
Weekend, yeah. Let me stop this. I'm so sorry, guys, about the first part of class. I'll put up notes.